Mathematics Department of the Jagiellonian University. It is a great pleasure to have you here. And now you will listen to a mathematical talk. My name is Krzysztof Ciesielski. I work at the Jagiellonian University Mathematics Institute. I was asked by one of you what is my area of research and interest. I work as a mathematician in topological dynamical systems, which is kind of joining topology and differential equations, but I work generally from topological point of view. Also, I am interested in the history of mathematics, and I work for many, many years in popularization of mathematics, writing articles, books, talking about mathematics, to say general audience. The title of this talk is on some non-standard mathematical problems. My purpose is to present you some mathematical problems which in formulation are not difficult. In formulation they are completely elementary. Also, they have quite elementary solutions. But these are problems which are not easy. When one sees a solution which is in fact very simple, one could say, ah, that's very easy. But to see easy solution is not the same to find that simple and easy solution. So I will say about some such problems. This topic of the talk has one extra advantage. If one of you is tired, sleepy, or is thinking about something more interesting in mathematics, of course, one could not imagine if there is anything more interesting than mathematics, but if someone of you has something, or perhaps for a moment something is too boring, any problem, after 1, 2, or 3 minutes, we have the next problem, which is completely independent from the previous one. So, if you don't understand or if you don't listen to one problem, after a couple of minutes, you can join the lecture and listen to the next problem. So, I hope every one of you will find something interesting here. Before I will show you these problems, let me say about some pictures. As every one of us knows, mathematics is beautiful. And there are people who demonstrate the beauty of mathematics and they love mathematics. Unfortunately, not everyone has the same feeling on mathematics. But what's good for us that the lady who demonstrated this wrong attitude to mathematics didn't agree to show her face. Let's say about some mathematical problem. You know Pythagoras theorem. Of course, it is a problem for Pythagoras theorem, and one has to find x. But there are a non-standard solution to this problem. Yes. Find x, and this is the answer. Let's go to our problem. The first one is connected with this year, 2014. 2014 football teams take part in the competition to win the Gold Cup. The teams play each Saturday. This is a single elimination tournament. That is, a winner of match will play next week, and a loser ends its participation in the competition. In the case of draw, which in football may happen, executing penalties determines the winner. Just like in European Championship or World Cup, which is going to take in Brazil, and so on. In such system, when the draw is, the winner must be determined. So, on first Saturday, 1,007 matches is organized, and 1,017 loses, and 1,017 go to the next round, and so on and so on. But what happens if one Saturday the number of teams is odd, just like this next Saturday when 1,007 teams play? Then one team, determined by the drawing, is promoted to the next round without game. And in the final game, 2 teams play, and one of them, the winner, gets the gold cup. This is the situation. And the question is, how many matches has to be played to determine the winner of the cup?
Matches have to be played. No, there's a mistake. Have to be played.
No. They were strongly invited, but they didn't want to.
Are you solving it?
Of course, it is not difficult to count. The first Saturday we have 1,007 matches. Then, next Saturday, one is promoted without game, 1,006 plays. We have to divide it by 2, it is 503. 503 plus 1 is 504. So next Saturday, 252 matches and so on and so on. And we have to add it, and in the end, we have the result. But, you know, there are many additions to do, and it is not difficult to make a mistake. Although, now, there is 2,014 teams that play. But perhaps one day 70,100 teams will play. Or we'll have a competition where every citizen of Poland is going to play. So on, so on, so on. So the counting will be rather boring, tiring, and easy to make a mistake. But the solution is very, very simple. The answer is 270. Why? Note that after each match, one team loses and does not play more. At last, one team wins. So after each match, one team loses. So what is the number of teams? The number of matches. It is the same number as the number of teams that lose. Only one team does not lose at all, this one who gets the cup. So there were 2014 teams and 2013 of them lost. Each lost once. So the number of matches is 2013. And it doesn't matter if there were 20 teams or 50,000 or 50,000. If you are interested in tennis championship, so it is the same rule. In tennis championship, the number of matches is just the number of players minus 1. Very simple solution. But I know plenty of people, including mathematicians, who try to count. Okay, next problem. This is a problem with a fly and a cyclist. A fly and a cyclist start simultaneously from the city A to the city B. The fly flies with the speed 20 miles per hour, and the cyclist rides with the speed 10 miles per hour. So, then here is the city A, and here is the speed. As you see, the fly flies quicker. When the fly arrives to B, it goes back to meet a cyclist. When it meets a cyclist, it goes back to reach B, then goes back, and so on and so on. So it goes, the cyclist rides just directly here, and the fly, bing, 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 all the time, shortest distance. The story finishes when a cyclist and a fly arrive to B. The distance between A and B is 40 miles. How many miles did the fly? Of course, the first thought is to count it. But first, second, shorter, it is not easy calculation. But also, this has a very simple solution. You know that the way of the cyclist is 40 miles, and the cyclist all the time goes with the speed 10 miles per hour. So the time of the cyclist journey is just 4 hours. But this is also the time of the flying journey, which goes all the time with the same speed. So the time of the flight journey is also this 4 hours, but the flight flies with the speed 20 miles per hour, and this is 80 miles. And this is the solution. And this is very simple. Perhaps I will tell you one anecdote, a story about the great American mathematician Norbert Wiener, who once was asked this question or similar one by somebody, non-mathematician. And he got this question and he answered immediately. So the man who asked him this question said sadly, "Ah, you knew this puzzle." And Wiener said, "Of course not. I just counted very quickly the sum on infinite series." Now we have other two problems. There are 40 students in the department. Could we find 2 of them who celebrate their birthdays on the same day? Of course, yes. Because possible days of birthday is 366. Another question. Are there in this room 2 persons born on the day with the same number? We do not bother amount. That is, we are interested only in 1, 2, 3, 31. I'm sure, yes, let's make an experiment. Who was born on the 1st of Somas? Please hands up. Oh, start, ho, 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 how many of you? No, so we have. And of course, this is also easy to notice that the answer must be yes, because there are 71 numbers to be chosen, and the group of you is more than 31. So this is quite an obvious property, but this obvious property has its name in mathematics. Its name is Dirichlet pigeonhole principle. What is Dirichlet pigeonhole principle? If n plus 1 or more items are put into n drawers, then at least one drawer must contain at least 2 items. Obvious? Of course. The number of items is greater than the number of drawers. For example, here we have 2. There are boxes, not drawers, but we are mathematicians, so we may imagine that these boxes are drawers. So we have 3 balls into drawers. There is a box with 2 balls. Now we have 8 balls, 8 drawers, 9 balls, and here we have 2. There is not enough room to have all the boxes with only 1 or less. So this is quite obvious property. And it is known as Dirichlet pigeonhole principle. In Poland we say Dirichlet drawer principle. In German it is Schubfach principle. What is the reason of the name? Pigeonhole is in the United Kingdom something like that. There are pigeonholes. They are maybe interpreted as holes of pigeons, but in fact they are nothing to do with these birds. In universities, institutions, every member of staff has its shelf, which is called pigeonhole, his or her name here, and if somebody is going to put a letter or message to this member of staff, just put here. We have also such kind of pigeonholes here on the left-hand side from the main entrance, but they are closed by keys. This is a mathematician who gave the name to this principle. Johann Peter Gustav Lejeune Dirichlet. He lived in 19th century. One could ask, that's impossible. this is so simple property, so easy, that it is impossible that it appeared in mathematics only in 19th century. And of course, it is, in my opinion, obvious that it must have been noticed much, much earlier. But what's the point? As far as we know, Dirichlet was the first mathematician who distinguished this property separately and wrote about this with the property as it sounds in mathematical paper. He wrote a paper about numbers and he used this property and formulated it, and he used the name Schubfach principle about drawers. The name of drawers is originated by Dirichlet. And definitely, even in papers, it is almost sure that somebody used the property earlier, but Dirichlet was the first one who just distinguished the property. But this is obvious, but sometimes it helps in not so easy problems. This is one which we are not able to check out in practice. Do there exist at least two non-bald people, bald means without hair at all, in Kraków, our city, with the same number of hairs on their heads? And this is, if people are not bald, this is impossible to check in practice. Look at your neighbor. Could you count the number of hairs on the head of your neighbor? I think even if the number of hairs is not extremely large, counting of them would be rather impossible. I do not think about bald people because then it would be easy. So we solve this problem using Dirichlet principle. Let's try to think out how many people can a man or the ladies have on his or her head. Of course, when you look at your neighbor's head, you see that these hairs may be seen separately. So definitely, for 1 millimeter square, it is not more than 5 hairs. In fact, less, but not more. How large area can be covered by hair? Not more than 25 centimeters times 25 centimeters. So now multiply this. 625 times 100 times 5. This is 312,500. And how many citizens has Kraków? In Kraków we have about 750,000 citizens. Of course, among them we have more than 400,000 which are not bald. I don't know how many bald people is in Kraków, but for sure not more than 100,000. So we have greater number of citizens than a number of possible hairs on the head. So definitely there are two people in Kraków with the same number of hairs on their heads. I do not know who they are, and nobody knows, but they are. Another problem. Let's first say definition. We call people A and B colleagues if A knows B and B knows A. So the relation of knowing each other must be symmetric. What I mean, for example, I do not know who is very famous in your countries, but perhaps almost all of you know who is, say, Barack Obama. You heard about him, you saw him by TV, and he is quite famous, as each president of the United States is known. So let's say you know Barack Obama. But does Barack Obama know personally any one of you? One, okay. But definitely there are more people here who know Barack Obama. So we mean, let's say, colleagues if they know each other. And I say that in this room, you are from different groups and you do not know each other, all of you. There are two people now who have the same number of colleagues. I am sure. Of course, now it is easy to solve Dirichlet principle. Great. But how many colleagues may have a person? Imagine that in the room now is 70 persons. I do not know precisely how many of you, but it's quite probable, say, assume that it's 70. How many colleagues may have one person? 0, 1, 2, 69. If there is someone of you, very lonely person who does not know anyone else, in English we call such a people loner, so loner does not know anyone. But maximum number is 69. Somebody very active, say a doll who knows everyone. And how many numbers of possible numbers of colleagues we have? From 0 to 69, it is 70 possible numbers. This does not fit Dirichlet principle, because we have 70 persons and 70 numbers. But this is possible to solve. How? Note that the numbers 0 and 69 cannot appear simultaneously. Why? Because there is a loner who does not know anyone else. There is not a doll who knows everyone, because he does not know this loner. So either 0 or either 60 or 69, simultaneously 0 and 69 are impossible. So we have two possibilities, or blue possibilities from 1 to 69, or green possibility from 0 to 68. In both cases, we have 69 numbers as 70 persons. So there are two persons with the same number of colleagues. Okay, now I am going to make an experiment. I would like to ask 6 of you to stand up. I am not going to fight with you, it is nothing dangerous. I just want 6 of you to stand up. 1, great. Stop. 1, 2, 3, it's too much at the moment. So, okay, 7, 6, maybe, okay. And no, 7. Okay, great, 6 persons. And I say that among this group, people in this group, there are either 3 people who know each other, or so say colleagues, or 3 people who do not know each other in person. Let's try. Try to answer this thing. Do you know each other? Yeah. Oh, so I have these 3 people who know each other. Thank you very much. Thank you.
Well, all right.
So the problem shows that among any 6 persons, we may find 3 of them, such that either each pair of them, that those 3 are colleagues, so know each other, or each pair of them, that is of those 3, are non-colleagues. But before I am going to solve this problem, I will present you an example. In the University Chess Championship, 6 persons were qualified to the final. In this final, each pair of them plays 1 game. The players play games either in maths department here, or in chemistry department, which organized this excursion where we have a group here. Show that we may find 3 players, A, B, C, who play all the games between them, that is A, B, A, C, B, C, in the same building. Either in math department or in chemistry. Before, I'm not going to solve this problem separately. I will solve another problem from which these two will be simply conclusions, simply correct. What is this problem? Consider 6 points, the vertices of hexagon in the plane. 1, 2, 3, 4, 5, 6. And I am going to join these points and paint them either red or green. And prove that there is a triangle with the vertices in some of given 6 points which has a segment of the same color. Let's try. First segment, please tell me. Red or green?
Green.
Green.
It won't be seen. It won't be seen.
Green. Next one, next person.
Green again.
Green again. This one, next person.
Red.
Right. No.
No.
There are 2 colors. I do not have blue chalk in my hand. Red. Red. Okay. Next one, next person.
Green.
Green. Green. Next one, next person.
Blue.
No.
There is no blue, green, or red.
Red.
Red. This one, next person.
Red.
Red. This one, next person.
Green.
Green. Green. This one, next person.
Red.
Red. This one, next person.
Red.
Red. This one, next person.
Green.
Green. This one, next person.
Red.
Next person. Who's next person? Red. Okay. This one, next person.
Green.
Green. Green. This one, next person.
Red.
Next person, I said. This one, next person.
Green.
Green. Green. I think that's all. And you see, I have green triangle.
There's one.
You see? Well, here I have the red triangle. But of course, the reason is I asked people here to pick up suitable colors before. Nevertheless, if this is true, then we have these 2 problems solved. 1. Take any 6 persons from the room and interpret them as points, and join them if they know each other by green, and if they do not know each other by red. If we have green triangle, we have 3 people who know each other in person. If we have red triangle, we have 3 people who do not know each other. Okay, what about second problem? Again, imagine these players as points and join them in mathematical department by green and in chemistry department by red. And we have green triangle means that we have 3 players playing in maths department. And if we have red triangle, we have 3 players playing in chemistry department. So now, the only problem for us is to solve this problem. Okay. This also goes to Dirichlet principle, and I will formulate slightly different but also obvious version of this principle. If 2n plus 1 or more items are put into n drawers, then at least one drawer must contain at least 3 items. In particular, take n equals to. If 5 items are put into 2 drawers, so at least in one drawer must be 3 items, of course. And now let's go to our problem. We have 6 points and pick up one of them. Say this. From this point, we have 5 segments joining others. And if we have 5 segments, then 3 of them must be painted the same color. Say green. And now, consider this segment. If it is green, the problem is solved. So it must be red. Next, take this. If it is green, the problem is solved. It must be red. And now we take this. If it is green, the problem is solved. So it must be red. And this is the end. This problem appeared in the Mathematica Olympic Games in Poland for secondary school students long time ago, and the number of students who solved the problem, they had 3 problems for 5 hours, was not large. Now, we will move to another kind of problems. Problems with coloring. Consider the chessboard 8 times 8 without 2 opposite squares. We cut off these 2 squares. Is it possible to cover this chessboard by 31 domino pieces, and each piece covers 2 squares? Of course, you know how domino looks like. It is something like that. And if it is the classical chessboard, 8 times 8, it is not difficult to see this off. This is one of possible covering of this chessboard. Say 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, but if we wanted to cut off these opposite squares, and we try to cover chessboard by domino pieces, it would be not so easy. In fact, it would be impossible. But if we cannot do this, this is not a reason to say, it is impossible. There are many things which I cannot do, but others can. So, mathematically, we should prove that it is impossible. And how to prove it? The hint is, remember that there is a chessboard. In chessboard, we have squares painted black or white. And now, notice what's going on. We have, in this new chessboard, 32 squares black and 30 squares white, because these 2 I cut are of the same color. And notice that however we put domino piece in the chessboard, each covers 1 black square and 1 white square. So, this is the solution. It is impossible to cover chessboard by domino pieces because it should have covered 31 black pieces and 31 white pieces. Next problem, very similar. Can a chess knight, in Poland we call this chess figure a horse, like that. Can a chess knight make a route from the upper right corner square to the lower left corner square of the chessboard 8 times 8, staying on its way precisely 1 on each other square? To solve this problem, we need to know something. We need to know how a chess knight moves. Several of you definitely know it, and I'm sure that several of you does not know it. What is the move of chess knight? It is something like this. The chess knight stays on the square. 1, 2, 3, rest. 1, 2, 3, rest. So he moves twice, then turns left, turn right, once, and rests. Here we have a knight, and these are indicated by crosses all the squares where this knight can move from this place. Okay, and it is easy to notice that from black square it moves to white square, and of course from white square it must move to black square. And again, this is the hint how to solve this problem. After each move of a knight, the color of the square taken by a knight changes. If he was on black, next he was on white, next on black, and so on and so on. And now, this is a chessboard 8 times 8, so we have 64 squares. According to our assumption, it has to make 63 moves. Why? Because in the beginning, he stays on one square. After the first jump, he has 2 squares taken in his route. The first one and the second. After the second route, 3 squares. After the fourth route, 4 squares and so on. And after the last move, he had all the squares taken, each one once, so it must be 63. So if he changes color in each movement, if he started from black, he must finish in white. But this square is also black, so it's impossible. Look, we proved more. We proved that in this way, the knight who starts here cannot finish its way here and here and here. If possible, he may finish its way only in white square. And in fact, it's possible to prove that for each white square, such a route exists. Okay, we have horses, now let's have frogs. On each square of the chessboard, 8 times 8 is 1 frog. In one moment, when the signal is given, say, each frog jumps to one of neighboring squares. May happen that after 64 jumps, each square will be taken by precisely 1 frog. Let me explain what is neighboring square. We have a frog on the chessboard. By neighboring square, I mean this form. The frog cannot jump on diagonal, only left, right, up, down. This is neighboring square. So we have on each square a frog. I say signal or claps or something like that, and then each frog jumps to neighboring square. Of course, it may happen that 2 frogs will jump to the same square. It's possible. But my question is it possible that after this jump, also each square will be occupied just by 1 frog? And the answer is simple. Of course, yes. Why? We have this chessboard divided into such columns, and then join this in pairs. This with this, this with this. And if the frogs just change their position according this way, after this signal, on each square there will be just 1 frog. So it is possible. But the next question is not so easy. What about the chessboard 7 times 7? Here, dividing it onto such pairs is impossible because, let's try, 1, 2, 3, and here we have 7. 1, 2, 3 pairs, and something left is left. So this method does not work. But this method does not work, does not mean that it is impossible. But it is impossible, and of course, what is the reason? Colors. Color. Note that after a jump of the frog, the color of the square taken by the frog changes. If the frog was on white square, it will be on the black square, and simultaneously. And in this chessboard 7 times 7, we have 25 white and 24 black. So we have the solution. After the jumps, 25 frogs that were on the white squares will have to take black squares. 25 of them were on the white squares. Now they will take black squares. But there are only 24 black squares. So definitely after the jump, 1 black square must be taken by 2 frogs. I also use Dirichlet principle. But this is it. Now, the last problem concerning column. Can we cover the chessboard 8 by 8 by 16 stones 4 times 1 presented in the picture? 8 times 8. The answer is easy. Yes, of course, no problem. Here is, it is shown, we have parallel stones, 8 on the left, 8 on the right, very simple. So, of course, it cannot be the problem I am going to pose. The problem is, what about the chessboard 10 times 10? Where are 25 squares? Ha! We know coloring. But if we color this chessboard, this will not work. Why? Because every stone 4 times 1 takes always 2 black and 2 white squares. This will not work. There will not be any contradiction. But nobody say to us, you must color the chessboard in classical way. Let's color it in another way. Like that. One, three, 1, 3, 1. Then we move here. 1, 3, 1, 3, 1, and so on. And know what's going on. We have 25 stones, as we have in the chessboard 10 times 10, 100 stones. We have 25 stones. So, know that each stone covers 1 blue square. It doesn't matter if it is put this way or this way, it is put vertically or horizontally, it always takes 1 blue and 3 white, yes? We have 25 stones, so there must be covered 25 blue squares. And how many blue squares is here? Yes, 26. 10, 6, 6, 2, 2. 10, 8, 8, 26. Impossible. When I am saying you about these problems, you see that it is not so difficult. But I assure you, it is not easy to find such solution without knowing these tricks. Well, in the end, finally, I am going to present you 2 problems more concerning classical mathematics. 1 geometrical problem and 1 problem with numbers. The first one is geometrical. In the rectangle A, B, C, D, the points P, Q, R, S are midpoints of the segments A, B, B, C, C, D, and D, A. So P, C, R, S are midpoints of these segments. The point T is the midpoint of segment SR. And I draw a triangle. Right. The area of the rectangle is 24. The problem is find the area of the triangle PQ. Why I am going to tell you about this problem? I am going to tell you to show that sometimes it is very good method in solving geometrical problems to draw something extra. And I am going to draw such lines. Then, as these points are segments, are midpoints of this segment, we have here parallelogram. And now we can draw these parallel lines from the point T in this parallelogram. The red parallelogram is divided into 2 smaller parallelograms. And this segment divides this parallelogram onto two equal parts, and this segment divides this parallelogram onto two equal parts. So the area of black triangle is the half of the area of red parallelogram. And what is the area of the red parallelogram? It is also simple. Let's draw blue line. Here I have a rectangle, and this part is half of this. These two parts are equal, and the same is in these four rectangles. So we have that the red parallelogram has the area equal to the half of the area of the gray parallelogram. And the black triangle has the area which is a half of the area of red parallelogram. So 24 divided by 2 divided by 2, the answer is 6. But when you see this without this additional line, it is not so easy to introduce the solution immediately. But when you see this, the solution comes to you immediately. And the last problem, I started with the problem connected with this year, 2014, so I will finish also with the problem connected with the year 2014. What is the last digit of the number? 2014 to the power. The power is 2013 to the power. The power is 2012 to the power, and so on and so on and so on. Do not try to count it. It is a very, very, very large number. I expect that your computers will not manage. But we can answer the problem. Here, I am going to say something which also appears in mathematical problems. Sometimes we have too much assumptions which makes the problem more difficult. Remember the first problem with the football matches? I was saying about this, that they are drawing a lot, that they play each Saturday and so on. And in fact, it doesn't matter. It was the rule how the players were chosen to play the next match was not important. The important was only this. The team that loses does not play again. And that was everything. The timetable of the schedule of the competition was not important. And here also we have something not important. You know, if I am going to the last digit of the power, in fact, 2014 is not interesting. For the last digit, only this form makes influence. So, we have simple problem. What is the last digit of the number? 4 to the power 2013 to the power 2012 and so on. It is easier. However, the number is still very, very large. But I have the number 4 to any power. I do not mind which one. 4 times 4 is 16. 16 times 4 is 64. And so on. But concerning this, I am interested only in the last digit. 16 times 4 is not interesting for me. 6 times 4 is interesting from the point of view of the last digit. So I 4 times 4, 60. 6 times 4, 24. Then 4 times 4, 60. So the number which appears there is 4, something and 6, something and 4, something and 6, and so on. So I can notice that the last digit of 4 to the nth power is 4 if n is odd. And the last digit of 4 to the nth power is 6, oh, sorry. It should be 6 here, I'm very sorry. Here is 6. imaginary 6 if n is 11. So, our question is only what is this number? It is 2013 to some power. But 2013 is an odd number. It doesn't matter what is the power. An odd number to any power is an odd number. So, answer is 4. And in the end, I started from some cartoons, so let me show in the end some other cartoons. Here you have a very untypical machine to draw right angle on the blackboard. Not common, and some cartoons. Write the largest number you can. And how the student answer? This is the largest number. A son says to his father, "These are the happiest years of my life, eh? You obviously haven't met my algebra teacher." This is guidance counselor. "No, I'm not interested in finding a career as of yet, but I would like you to find my math teacher a new one." Anthony, all over my new carpet, bad cat, bad cat. What did Anthony do? Bad cat Anthony do. This is what Anthony do. And in the end, my favorite cartoon, where one math teacher said to another math teacher, 5/3 of the class do not understand a word I'm saying about fractions. Thank you very much.